All right. Well, good evening, everyone. How y'all doing tonight?
Amazing.
All right.
Great.
It's another day stuck at home.
Yeah.
Actually worked from home today. It was pretty good.
All right.
Ready to go back to work now. It's a
All
lot
right.
easier to get things done. That's for sure.
Yeah. All right. So let's see here. Let's go back over to the lecture notes. Welcome to lecture number 17 for MT225 in our new format. Last time we started into the method of sections. And tonight we're going to do a little bit more practice on method of sections, but I have a couple problems we're going to work out. Let's go ahead and take a look at the lecture notes. There we are. So meetings, the Zoom meeting ID, I've reserved that one for the rest of the semester. So as long as you have that number, you should be able to get in. No password's been set or anything like that. So no need for that. The video channel is up there on YouTube. So if you want to check out the lectures or any of the previous example problems, those are all set up on the YouTube channel. I'll try to get those up right after class is over. Quiz 5, I actually did not get a chance to finish grading those yet. It's a little bit more difficult when you don't have the papers right in front of you. So because of that, if you still haven't submitted that and you want to, go ahead and do so. I'll put up the solutions probably sometime tomorrow, but
How do you raise your hand?
getting those graded here. I'll probably email you back grades. I'll try to do some markup on them, so if I can point out where issues are.
Put it in
But
the chat. Chat?
but
Where?
otherwise,
The orange one. This one?
the
I gotta raise my hand.
quizzes will be returned by email. And I have posted our new homework assignment. New homework assignment due at the end of class, essentially a little bit after the end of class, on Wednesday next week. So email that to me at my MVCC address. That way I've got a copy of it that I can get easily on my laptop. Be a little easier for me to grade that way versus text pictures.
Hey, Tom,
Yeah, go ahead.
I sent you an email already.
Yep.
Can you disregard that one for me, please?
I actually didn't. Yeah, actually, I can. I did. I think I did finally receive that. It took a little while to come through.
Okay. I'll be sending you a new one.
All right. Let's.
Have you guys? Oh, sorry.
No, go ahead, Mark.
We've been having issues where it's been taking hours, if not days, for emails to go through because of the traffic lately. I don't know if you're experiencing the same thing.
I haven't seen much of a delay, but at least everything I've been expecting to come through has come through for the most part. But it's possible. I'm not gonna hold anyone really hard and fast to deadlines by email.
Okay.
I mean, especially given the situation. I'm happy if you've gotten the work done.
Gotcha. All right. I just wanted to check if anybody else was having.
Yeah, it seems like MVCC server's been fine. I haven't seen any issues with my personal servers, but there is a lot of extra load out there these days. All right, so homework, well, we haven't really had homework. If anyone has any residual homework problems from our previous assignment from the method of joints problem, method of joints homework, now would be a good time to ask. But if not, the solutions are up for that. Today we're going to do some more method of sections practice, and we're just going to start up with a problem. There's not really much in the way of new notes or anything tonight. We'll just go over to the document camera and work through a problem. Be sure as we're working through the problem here to follow along. If you got any questions, go ahead and raise them up. I'll try to get to you as quickly as possible. I'm not going to be looking directly at the screen, so I won't necessarily see the little raised hand icons that they have here for that. But if you just speak up, I'll be able to interrupt and hear you. So let's go over to the document camera.
Are you going to be giving us homework?
Homework is posted on the website. Homework 7, the new homework assignment on method of sections, is posted up on the website.
All right, and that will be due Wednesday of next week.
Yep, Wednesday of next week.
All right.
All right. So the first problem here is going to look similar to the first problem on the homework assignment, on the new homework assignment. And it's something we've worked at a couple different places before. We've worked this kind of problem. It's going to be a truss supported on a wall. So here I've got my vertical wall, and we'll put a, I really missed my whiteboard. Let's try that again. So here's my vertical wall. And we're going to put a truss on there. We'll put a pin support up here, a roller support there. And let's see, we'll have a couple of bays here. Something that looks like that. Right from here, we'll hang a 20 kip load. Put some geometry on it. We'll have three bays at 5 feet each. And we'll have our vertical section here at 8 feet. And we'll label out some of the joints here: A, B, C, D, E, F, G, H. All right, so there's our problem. And for this one here, let's find out what's going on right in the middle of the truss. So we'll look at what's going on in these three members right there. So we want to find members BC, BF, and FG. So that's what we'll fill out in our table. Members BC, BF, and FG. We'll have our load and kips, whether we're in tension or compression. So there's the problem. And this will be a nice problem to work with the method of sections, because method of joints would require that we do a lot of work to kind of walk into the middle of this truss. One of the benefits of the method of sections is you can jump right into the middle of a truss and figure out what's going on with the members before you solve other joints. You don't have to get a bunch of unnecessary information. Of course, with any of these methods, the first thing we have to do is solve the external problem. We've got to figure out what the reactions are at our supports. We need those to be able to proceed. So I'm going to scroll this down just a little bit here and draw a free body diagram of the truss as a whole, ignoring the internal structure, just looking for the reactions. So our truss looks something like this, just a rectangle. If we just think of it as one big solid object, for solving the external problem, all we ever have to worry about is the external forces. We don't have to worry about all the members inside and what the actual structure of the truss is. We just have to worry about the forces applied to the outside. So we have our 20 kip force applied at the lower right corner. At A, we've got a roller, and a roller support only exerts a force perpendicular to the surface that it's on. Since our roller sits on a vertical surface, it's going to have a horizontal reaction. So we'll call that RAX, keeping our traditional coordinate system. of x positive to the right, y positive up, and counterclockwise moments positive. At h, we've got a pinned support, and a pinned support can contribute two forces, an x direction reaction, which I'll call RHX, and a y direction reaction, RHY. Those are all the external forces, the two sets of forces at our supports and our single applied 20 kip force. And we'll pull any geometry we need off of the original drawing when we need it. So let's solve the external problem here first. The external problem is a non-concurrent force problem. So we have to take our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point equal to 0. So let's do our sum of forces in the x direction. Looking through the four external forces on this truss, only two of them are in the x direction. And based on the directions I've assumed, I've got a positive RAX and a positive RHX. And that sum's got to be equal to 0. Unfortunately, we can't really do anything with that equation just yet. There are too many unknowns. Two unknowns, one equation, can't do much with that. So let's try our y direction equation. Sum of forces in the y direction. We've got a positive RHY and a negative 20 kips. And to be in equilibrium, that would have to be equal to 0. That equation we can solve right away. RHY must equal 20 kips. So we've got one of our reaction forces. RHY is 20 kips. Came out positive, so the assumed direction was good. I assumed it was pulling up, and it actually is. So came out positive. Unfortunately, that doesn't help us with our x direction equation. So that's why we need our moment equation. So we'll take our sum of moments about a point, and you could pick either point H or point A as your pivot point. Those would work out pretty well. Either way, you're going to knock out two forces. If you picked your pivot point at A, RAX won't have a moment, RHY won't have a moment. If you pick H as your pivot point, RHX and RHY will both not have a moment. So let's pick H, just sort of arbitrarily here. If I pivot at point H, RHX will not have a moment, RHY will not have a moment. RAX will, and the 20 kips will. And be especially careful to make sure you're clear on what the arms for these forces are. The distance that I've got here, I had in my original problem 3 bays at 5 feet each. So this is a distance of 15 feet. And then I have this distance here as 8 feet. That's the geometry we'll need in order to figure out our moments, because moments are always a combination of force and distance. So let's look at RAX first. RAX is definitely going to cause a moment. So we need to have RAX there, but we got to have an arm for it. The arm is the distance between the line of action of RAX and the pivot point. The pivot point's up here at H. RAX is down here, and its line of action is horizontal. So this distance is the distance that we need for the arm, and that's 8 feet. So we have 8 times RAX. We've got to figure out whether that's positive or negative. If we pin at H and push to the right at A, everything's going to want to rotate counterclockwise. Counterclockwise moments are positive. So that should be a positive 8 RAX. Then we have the 20 kip force. We've got our 20 from the 20 kips, but now we need an arm. The arm is the distance between the pivot point and the line of action of the force. So our pivot point is here. Line of action's over here. The distance there is 15 feet. So we have 15 as our arm times 20 kips of force. We have to figure out whether that's positive or negative. If we pin at H and we pull down here where that 20 kip force is, we're going to get a clockwise rotation. Clockwise is negative. So there's our moment equation. Now, fortunately, the moment equation, pretty easy to solve. In fact, if you ever get a moment equation with more than one unknown, you did something wrong. In this class, it's consequence of being in 2 dimensions, essentially, that we should always be able to pick a pivot point that results with one unknown. So if we multiply things out here, we've got 15 times 20 is 300, so we have 8 RAX minus 300 equals 0. If we add 300 to both sides, we have 8 RAX equals 300. Divide both sides by 8, and RAX comes out to be positive 37.5 kips. So RAX is 37.5 kips. Knowing that, we can go into our x direction equation now. We have 37.5 kips plus RHX equals 0. Solving that would mean subtracting 37.5 from both sides. So that'll tell us that RHX is a negative 37.5 kips. That negative is important. That negative tells us that we guessed wrong. I assumed RHX was pushing to the right, but the math is telling me that that assumption was wrong. I got a negative result. So correctly, RHX should be to the left. So if I add my arrows here into my reaction forces, RHY was 20 kips up. RAX was 37.5 kips to the right. RHX is going to be 37.5 kips to the left. So there's the external problem. We figured out the external forces on the truss. So we've got 3 pieces of information about our supports. Anyone have any questions as to how to get the reactions at the pin and the roller support? All right, so let's jump back to the original problem here. Now we can copy in that information that we had from the external problem. We have RHX is 37.5 kips to the left. RHY was 20 kips up. And RAX was 37.5 kips to the right. So now we can do our method of sections. And the way we do method of sections, we have to find a boundary, a system boundary. We need to essentially wrap part of the truss in a bubble and look at the forces that are exerted on that part of the truss that we're isolating from the rest of the world or the rest of the universe. As long as we can make part of that bubble cut through only 3 at most unknown forces, then we can solve a method of sections problem in one set of equations. We do have to close the bubble. This is only a piece of it that cuts through the surface. We have to close the bubble either to the left or to the right. Either way works, and either way involves basically the same math. So I'm going to close to the left on this one. So when I close it to the left here, I'm going to draw through the supports. So everything that's enclosed in that little bubble, that is my universe. That is everything in the universe. And what we're looking at is what has to push on the edges to keep that piece in the bubble in equilibrium. Go ahead, Mark.
So what is your deciding factor whether you choose the right side or the left side?
Um,
Is there like a method to your madness, or is it just
no, not really. I'm just
luck of
we
draw?
closed to the right on a couple of them last time, so I'm closing to the left on this one just because.
I was just wondering if there's like something you're looking for
Nope.
in particular that you think it'll be easier
You know,
or harder.
usually I'm looking for whether or not it's going to be basically how many forces I'm going to have to deal with, and
Okay.
I'm always going to get 3 forces from where I cut through.
Yep.
And then if I'm cutting through the supports, I'm going to get some amount
3
of,
more.
I'm going to get 3 more here. If I close to the right, I'd only get 1 more. So it might have been a little bit easier to close to the right in this one. But then in this type of problem, if we had looked at this a little bit ahead of time, you might have noticed that if you close to the right, you don't actually need the reactions at the supports. If you close to the right, then we wouldn't have had to bother solving that external problem. But in the vast majority of cases, when we have a problem where we're sitting a truss more like this, more vertically, where this is the ground, we usually
Yep.
don't have a choice in the way that we in closing the truss or closing the bubble. We usually either have to go through one support or the other. So just to give a little bit more practice in using the information that we get from our external problem, I closed to the left on this one, but you could have closed to the right and you would have gotten the same answer. And in fact,
Okay.
if you're getting this pretty well, go ahead and work it out on your own to the right and make sure you get the same answer that I do. In fact, it's kind of a better answer that way because it's doesn't involve things that were calculated. There's a little bit of round off error. Well, this is perfect right now, but if these had been rounded off, we would have had a little bit more error in there. But in the end, it doesn't really matter which side you go
Okay.
to, and substantially the calculation is about as difficult as it would be otherwise.
Okay.
So let's go
Thanks.
ahead and close to the left here. And when I close to the left, I've got to redraw my free body diagram, but just of what's enclosed inside the bubble. So inside the bubble, I get joints H, G, I get joint A, and I get joint B, and then I get a piece of member FG, a piece of member BF, and a piece of member BC. So this is where I've cut through. I've cut through these 3 members. If at the instant I cut through, I apply exactly the right amount of force on that member, let's say FG here, or FBF here, FBC here, that will hold the rest of the truss in equilibrium. These 3 forces that we've now exposed by cutting through the truss represent the force that the rest of the truss exerts on the part of the truss that we're keeping. Now we've also got to put our reaction forces in the correct directions. So we had 37.5 kips this way. We had 20 kips up. And we had 37.5 to the right. So right there is the free body diagram for the section of the truss that we're keeping. And we've got 3 unknown forces. Fortunately, this is a non-concurrent force problem, so we have 3 equations that we can work with. We do need an angle. We need that angle right there. And fortunately, that's not too hard to get from up here. This is a triangle. Right triangle right there. 8 feet on the opposite side and 5 feet on the adjacent side. So if we take the inverse tangent of 8/5, we get 57.995 degrees. There we are, 8, 5, inverse tangent. Oops. Yeah, 57.995 degrees. So there we've got our angle. So since this is a non-concurrent force problem, we've got three equations we can work with: our sum of forces in the x direction, our sum of forces in the y direction, and our sum of moments about a point. Usually the x direction equation ends up being the ugliest one in these types of problems. We've got two x direction forces here, and then we've got another two here in our unknown and a piece of a third. So we're going to have 5 terms in our x direction equation. So just make sure we catch all of them here. We've got 37.5 to the left. We've also got 37.5 to the right. We've got all of FFG. We've got all of FBC. And then we've got a piece of FBF. It's the adjacent piece, and adjacent goes with cosine. So we have FBF cosine of 57.995 degrees. So that's our x direction equation. In the y direction, we've only got 2 forces with a y component. We've got the 20 kips up here, and we've got a piece of FBF, the opposite side, the sine piece. So we've got 20 kips up, so that's a positive 20. And then FBF pulls up, so it's plus FBF sine 57.995 degrees. So that one's not too bad. And then we've got our moment equation. You really have to be careful when picking your pivot point for the moment equation in method of sections. There's always going to be a point that works out to be best. And you always want to avoid having whatever forces are at angles, whatever unknown forces are at angles, you want to avoid those having a moment. The easiest way to avoid those having a moment is to pick your pivot point there. I would pick point B as my pivot point. If I pick B as my pivot point, that's going to knock out FBC and FBF. It's also going to knock out this 37.5 kips, since the line of action of that 37.5 kips goes right through B. But FFG will have a moment, the 37.5 kips will have a moment, and the 20 kips will have a moment. So I'll have 3 terms in my moment equation. So let's work those out. Here we've got let's work with FFG first. We've got our force, FFG. We've got to figure out the arm for that. Our pivot point is here. The force is up here. That's 8 feet away. The line of action of FFG is horizontal. That's 8 feet above where pivot point B is. So we have 8 FFG. And if we pin at B and pull to the right up there at G, we're going to have clockwise rotation. Clockwise rotation is negative. So we have negative 8 FFG. If we look at the 37.5 kips, that also has a line of action that is up here, horizontal, 8 feet away. So our arm for the 37.5 kips is 8 feet as well. But pulling to the left is going to cause a rotation that is counterclockwise. Counterclockwise is positive. And then we have our 20 kip force. The 20 kip force has a vertical line of action. The distance between the pivot point and that line of action is that horizontal distance there, that's 5 feet. So our arm for the 20 kip force is 5 feet. And if we're pinned at B and we pull up at H, that would cause a clockwise rotation, and clockwise rotations are negative. So there we have our equations. The moment equation and the y direction equation. That we can solve pretty quickly. Then we can plug in what we know into the x direction equation to figure out the last force. Anyone have any questions on getting up to the equations? All right. So let's go ahead and solve these here. Start with the moment equation. The moment equation, we'll go ahead and get some numbers here first. We've got 8FFG, negative 8FFG. We have 8 times 37.5, which is 300. So we have a positive 300, minus 5 times 20, which was 100. So we have negative 8 FFG plus 200 equals 0. If we subtract 200 from both sides, then we have negative 8 FFG is negative 200. Divide both sides by negative 8. Don't forget about that negative. So we divide both sides by negative 8. And FFG equals 25. And the units are kips. And it came out positive. So we have positive 25 kips. Positive means our assumed direction was correct. So we can go up to our table here and fill in 25 kips. We have to figure out whether that's tension or compression. The answer came out positive, so that means our assumed direction was correct. And the way that I drew the force here, I drew it as pulling on this little piece of member FG that was left behind. A pulling force is tension. So since it came out positive, member FG must be in tension. We can go ahead and solve the y direction equation by subtracting 20 from both sides. That'll give us FBF sine of 57.995 degrees equals negative 20. Really have to be careful about tracking your SIGN signs with these. If you lose a sign, that'll change your interpretation of whether it's tension or compression. So be really careful in the algebra. Divide both sides by that sine of 57.995 degrees. And FBF comes out to be, looks like negative 23.585. So FBF, I'm just going to have to go up to the table here. It's 23.585, but it came out negative. That means that my assumed direction for BF was incorrect. I drew it as pulling member BF into tension, but it's actually pushing. Member BF is in compression. So member BF carries a compressive load of 23.585 kips. And then finally, we've got our x direction equation. The x direction equation simplifies a little bit because negative 37.5 and positive 37.5 cancel out. FFG was 25 kips. FBC, we don't know. But FBF was negative 23.585 times the cosine of 57.995 degrees. So you have to be careful here. When you get a negative answer, even though you might have interpreted what that negative means, in solving the algebraic equations here, you still have to plug in that negative value. I'm going to go to another sheet here to write that equation off a little bit more clearly. So our sum of forces in the x direction, we had 25 from our FFG. We had plus FBC, which we didn't know. Then we had a negative 23.585 cosine 57.995 degrees. And that was equal to 0. So that we can go ahead and solve. We'll key in some numbers here, 23.585 times the cosine of 57.995. So this piece here is a negative 12.500 to 5 sig figs. So we have 25 plus FBC minus plus a negative 12.55 or 12.5. 25 plus a negative 12.5 is a positive 12.5. So we have 12.5 plus FBC equals 0. Subtract 12.5 from both sides. And FBC comes out to be negative 12.5 kips. So it came out to carry a load of 12.5 kips. Remember, BC carries 12.5 kips. But it came out negative, which means my assumed direction from my free body diagram, my assumed direction is wrong. I drew it assuming that member BC is pulled on by the rest of the truss. The member BC was in tension. The math told me I was wrong. I got a negative value. So this has really got a push on member BC, meaning that member BC is in compression. So there we go. We found all three members. Those are the only three we needed in this one. We needed member BC, member BF, and member BG, or member FG. And we figured out that each is in, member BC and BF are in compression. Member FG was in tension.
Would you normally round to 3 sig figs up top
Yeah,
here?
if that was at that point, you can go ahead and do your rounding, unless you were going to use it for another calculation. If, for example, we also wanted to get member BG out of it, and we decided to do a method of joints at BG, you wouldn't want to round off BF because you're going to need that in the
Understood.
calculation. But if this was your final answer, then yeah, you could go and draw a final answer table with this rounded off to 3 sig figs. Now, if we look at it physically, the states of tension and compression kind of make sense here. If you think about pulling on this thing with 20 kips of force, pulling this down, the top of this is going to get stretched out. It's going to try to bend. And when things bend, the top, the outside of the bend goes into tension, and the inside of the bend goes into compression. So it should make sense that member FG is pulled on, is stretched out, while member BC is compressed. Think about those of you who have been through the A&P program. Think about what you know about sheet metal and doing bends in sheet metal, that the outside of the bend is in tension and the inside is in compression, or a wing lifting. The top of the wing is in compression, the bottom is in tension. So member BC, it kind of makes sense that it should be in compression, and member FG makes sense that it should be in tension. It's sometimes hard to figure out what these cross members are doing. But in this one, it's not too hard to figure out that as you're pulling this section down, it's got to squeeze on member BF. Member BF has got to be compressed. So that explains why member BF is in compression. It can be, if you've got multiple forces acting on this, if you've got multiple applied loads, maybe a side load here, it can be a lot harder to figure out whether a cross member is in tension or compression. But essentially, when you've got pure bending, it can be a little more physical to see what those cross members are doing. Anyone have any other questions on this one? All right. So let's try another one here. We'll do a typical roof truss problem. Let's take something that looks sort of like this. Pin support on one end, roller support on the other. Again, missing the whiteboard. We'll make this span 24 feet. We'll make the top here 6 feet off the ground. And let's see, we'll split it into 4 bays. So this would be 4 bays at 6 feet each. And then we'll do, let's say, something that looks sort of like that. And let's put some load on this. We'll put a right in the middle. We'll put a 30 kip load. And then let's say down here at D, we put a 8 kip load. And maybe we'll add a wind load in here too. So we'll put a wind load at F at 2 kips, just to make it fun. So there we go. There's the truss. So I'll give you a second to copy that down, as you might need to here while I take a drink.
What kind of beer you drinking though?
Just plain old water. See?
Poland spring beer.
Yes, there we go.
Just add some hops to it.
Yeah, there you go.
Looks like vodka from here.
All right. So just like all the other problems, we've got to do the external problem first. Let me identify which members we want here. Let's go with those 3 right there. We'll go for members BC, CH, GH, and we'll go for a 4th there. We'll do member BH also. So fairly complex problem, lots to it. So let's start with the external problem. For the external problem, I'm going to draw this again on another sheet, but without any of the internal structure, just a big triangle. We've got a pinned support at A. So a pinned support has 2 reactions to it, RAX and RAY. The roller support, I'm going to assume this is sitting on a wall, so it's able to have a vertical reaction, sitting on top of the top plate of a wall, typical roof truss. So that'd be REY. We had our 30 kip force here. right about there, we had 2 kips, and we had right around here 8 kips. Now we're going to need to know some distances here, and going back to the original drawing, the way this is set up, this point, after the way this typical truss, this is a pretty typical roof truss, and I forget the exact name for it, but there's actually a bunch of different names for roof trusses, and all the different arrangements you can come up with. But this is at the midpoint, so if the thing's 6 feet tall, this side load here is halfway up. It's at 3 feet. So that'll give us the geometry we need here, that the whole thing is 6 feet tall. It's 3 feet to there. And this one was we had 4 bays at 6 feet each, so we had 6 feet there, and then this would be 18 feet. So there we go. So there's the external problem. 3 unknown forces, RAX, RAY, and REY. Fortunately, though, nothing we have to break up in terms of sines and cosines. So we can just do our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. So let's go for the x direction forces. We've got RAX to the right, so that's positive RAX. RAY is up, the 8 kips is down, REY is up, 30 kips is down, the 2 kips is to the right. So we have +2. So that tells us right away RAX is a negative 2 kips. So RAX is 2 kips to the left. We assumed it was to the right, came out negative, so it must be to the left. So we've already nailed down one of our unknown forces. If we do our sum of forces in the y direction, we've got positive RAY. We've got a negative 30 kips. We've got a negative 8 kips. And we've got a positive REY. No other forces in the y direction. So cleaning that up a little bit, the negative 30 and the negative 8 is negative 38. Then I'd add that 38 to both sides, and I'd end up just fast forward a little bit through the equations that should be getting pretty familiar by now. That's what we'll end up with is RAY plus REY, the 2 forces pushing up, has to equal a total of the force pushing down. So 30 kips down. 38 kips down, excuse me. But unfortunately, we have too many missing pieces there. We can't go and solve for that just yet. So we'll need our pivot point, our sum of moments about some point. And just like a lot of the external problems, one of the supports is going to be the best place to go. May as well go at A. Just as easy to go at E. Either way works. So we'll pick our pivot point at A. That means RAY and RAX will not have a moment, but all the other forces will. The 8 kip force will have a moment. REY will have a moment. The 2 kip force will have a moment. Don't forget about that one. Easy to forget that that's there. And 30 kip force will have a moment. So we should have 1, 2, 3, 4 terms in our moment equation. So let's start just going kind of left to right here. The 30 kip force, its line of action's right down the middle. That's 12 feet away. So we've got 12 times 30. If we're pinning at A and pushing down at the peak of the roof, that's going to cause a clockwise moment, and clockwise moments are negative. Then we've got this 8 kip force that's 18 feet away. And similarly, if we push down here and pin at A, it's going to cause a clockwise rotation. So that's negative. We've got REY 24 feet away. But that's pushing up. If we pushed up and pinned at A, we get a counterclockwise rotation, so that's positive. And then we've got our 2 kip force. That 2 kip force has a line of action that is horizontal. So the arm is that distance right there. That's 3 feet. So we have 3 feet times 2 kips. Pinning at A and pulling to the right here where the pin support, where the wind load is, where at joint F. That's going to cause a clockwise rotation, and clockwise rotations are negative. So there we've got our 4 terms in our moment equation. And we've got the arms and forces. Again, still most common error I see with these is forgetting to put the arm with your unknown force. Well, that we can simplify down a little bit. We have negative 360. We have negative 144 plus 24 REY minus 6. So that gives us a total of 24 REY minus 510 equals 0. Adding 510 to both sides, we'll have 24 REY is 510. Divide both sides by 24. And REY comes out to be 21.25 kips. So it came out positive. So our assumed direction is correct. REY does push up with 21.25 kips of force. Now that we've got that, we can go to our Y direction equation. RAY plus 21.25 has to equal 38. If we subtract 21.25 from both sides, we get RAY is 16.75. So RAY is 16.75 kips. And that also comes out positive, so it's pointing up. Now, before we go and move on here, let's make sure that these reactions make sense. We have 2 kips to the left, meaning RAX has to pull on the truss to the left with 2 kips, and that makes sense to balance off the 2 kips that are pulling it to the right. The dominant load on this truss is right in the middle, that 30 kip force pushing down. And if that was the only force there, by symmetry, we'd be able to say that RAY and REY would both push up with 15 kips of force. So that we have something bigger than 15 kips of force here is a good sign for each of our answers. The 8 kip force is going to add to that. Now, if the 8 kip force were dead in the middle, then that would add 4 kips to both sides, and we'd have 19 kips on both sides. But it's more toward the right. It's more toward E than it is A. So more of that 8 kip sits on E than it does on A. That explains part of the difference between RAY and REY. The other part comes from this 2 kips pulling. That 2 kips pulling is trying to rotate everything around A, which is going to cause it to push down harder on E and try to pick up at A. So we get a little less load on A and a little more load on E as a result of that 2 kip side load. So our answers look pretty reasonable. So we'll copy those back over. Anyone have any questions on the reaction forces? So let's copy those back over here. RAX was 2 kips to the left. RAY was 16.75 kips up. And REY was 21.25 kips up. All right, so now we have to figure out how we're going to proceed. Now, I think in this case, the best course of action is going to be to do one cut, to do one method of sections problem, and then jump into method of joints at joint B to figure out BH. So I can draw a cutting surface right through those 3 members and get a pretty reasonable cut through the truss, only cutting through those unknowns. It'd be easiest, I think, in this case to close to the left, because if we close to the right, then we're catching a whole bunch of other forces that we'd have to deal with. Those forces are in there. They're all wrapped up in the reaction at A. So we still have those in there, but we can ignore them if we don't have to deal with them directly if we close to the left. So I think closing to the left to be the best path to take there, and that'll let us cut through those 3 members. And in the end here, we're looking for a table. Loading kips. And we have members BC, BH, CH, and GH. So let's draw the free body diagram of our section of the truss. So if we section off the truss, essentially we're cutting the part of the truss that is outside the bubble away and replacing that part of the truss with the forces that the part we're getting rid of applies to the part we're keeping. So we've got something that looks sort of like this. There's H. So we've got something that looks sort of like that. Or we've cut away these forces. We have to replace our pinned support with the forces it supplies. We have 2 kips to the left. And we have 16.75 kips up. This is the force exerted on member BC. This is the force exerted on member CH. And this is the force exerted on member GH. So there's the free body diagram of the section of the truss we're keeping. We're going to need some angle information here. Now, it turns out, and we can do all sorts of geometric proofs and things like this to prove that this is right, but it is correct that these 2 angles will be the same. Those 2 angles have the same value. You can argue it by similar triangles here, that these 2 triangles basically have to have the same fundamental shapes to them. So they all have the same geometry. This is 3 feet, that's 6 feet. And so you can figure out that the angles to horizontal have to be the same. We can figure that angle out by figuring out this angle right here. That angle there involves this big triangle right here. This big triangle that is 6 feet high and 12 feet on the base. So this angle, which would be the same as this angle and that angle, is going to be the inverse tangent of 6/12. So if we take our inverse tangent of 6/12, we get an angle of 26.565 degrees. So that's our angle. And we'll need that as we build up our equations.
Hey, Tom,
Yeah, go ahead.
can you do also 6/3?
I don't, well, yeah, you could do the 6/3 here. Yeah, if you know that's 3 feet and 6, you could do the same thing. I just kind of look at it as when you're doing roof trusses, things like that, you're usually looking at the peak height and then half the span if it's symmetric. So I just went with that one, but either way it'd work.
And just for clarification, all roof trusses, that's going to work for every roof truss.
For every, you can assume it's symmetric. You can build some asymmetric roof trusses, but they're pretty rare. Most of the time, we like each side to be the same.
Okay, just making sure.
Yep. Yeah, all those angles are basically going to be the same. So you could certainly take triangle ABH here and do 6 feet and 3 feet. You'll get the same answer. Inverse tangent of 3/6 is the same as the inverse tangent of 6/12. Any other questions on the free body diagram down here? All right, so let's scroll up a bit here and come up with our equations. So let's see, try and get that situated so we can see it. So let's do our sum of forces in the x direction. So in the x direction, we've got 2 kips to the left. We've got all of FBC to the right. Then we have a piece of FGH to the right. It's the adjacent piece. It would be the piece going to the right here. That's got to be the cosine piece. So cosine 26.565 degrees plus FCH, a piece of that to the right. Also the cosine piece. That's everything in the x direction. So like all the other method of sections problems we've done, the x direction equation is kind of ugly. If we do our sum of forces in the y direction, we've got 16.75 kips up, so positive. We've got a piece of FGH up. It's the adjacent piece, or the opposite piece, so it goes with sine. And then we've got a piece of FCH. That's down. Negative FCH. 26.565 degrees, so sine there. So we have the FCH pulling down, FGH pulling up, and we have 16.75 kips pushing up. So there's our y direction equation. And then we have our moments about a point. Always a good idea to think about your pivot point before you go and start calculating. if we picked A as our pivot point here, we'd end up in trouble because although it's not too bad of a trouble, I suppose, but it's ugly. We'd knock out FGH and FBC because both of those would have lines of action going through. But then we'd have kind of a complex moment to take here. We'd have to figure out what the perpendicular component of FCH is, or we'd have to kind of figure out what the distance is to that line. That looks like it's going to be a whole lot of trouble. Probably a lot easier to pick our pivot point at H. If we pick our pivot point at H, these forces at angles won't have a moment. FBC has a moment, but the arm for that's not too hard to figure out. The 2 kips and the 16.75 kips will have a moment, but those arms aren't hard to figure out. So being judicious about picking your pivot point can save you a lot of work in the end. So let's pick H as our pivot point there. That'll knock out GH and CH. BC, 16.75, and the 2 kips will have moments. So let's deal with BC first here. If the line of action of BC is down here, that is 3 feet away from the pivot point. So we have 3 FBC. If we're pinning at H and pulling in the direction we're assuming BC goes in, that's a counterclockwise rotation. Counterclockwise rotations are positive. So we have positive 3 FBC. The 2 kip force has the same arm, 3 feet. So we have 3 times 2. But if we're pinning at H and pulling with that 2 kip force, that would be a clockwise rotation. So that'd be negative. And then we've got the 16.75 feet, or 16.75 kips. That is 6 feet away. And if we're pinning at H and pushing up at A, that would cause a clockwise rotation. Clockwise rotations are negative. So there's our moment equation. Running the numbers down here, we've got 3 FBC minus 6 minus 6 times 16.75, which is 100.5. That equals 0. So 3 FBC minus 106.5 equals 0. And adding 106.5 to both sides, we get 3 FBC is 106.5, dividing both sides by 3. We get 35.5. So 35.5 kips came out positive. So that means that our assumed direction was correct. Member BC is really being pulled on by the rest of the truss. Member BC is in tension. So member BC carries a load of 35.5 kips in tension. Now that we know FBC, we can go back and use that in the other equations. But we've got a bit of a problem here. This is something we haven't run into yet, but it's something that you may have to deal with. Notice here our x direction and our y direction equations are tied together. They are simultaneous equations. You knew that was going to come back sometime, right? We've got 2 equations in 2 unknowns here. Once we plug in for FBC, we've got FGH sines and cosines. We've got FCH sines and cosines. Fortunately, they're not bad to deal with. We can clean these up pretty easily and solve them without too much difficulty. They're not as bad as they could be. But I'm going to have to go on to another sheet of paper to work with these. So prepare yourself for that. We can plug in that 35.5 up here. So we have 35.5 minus 2, that's 33.5. So our x direction and our y direction equations, if I copy those onto another sheet here so we can clean them up a little bit. -2 plus the 35.5, we've got a positive 33.5 plus FGH cosine of 26.565 plus FCH cosine of 26.565. That's equal to 0. That's one equation. The other equation is 16.75 plus FGH sine 26.565 degrees minus FCH sine of 26.565 degrees. So there we've got our two equations in two unknowns. So let's clean these up first by getting the numbers over to the other side. If I subtract in the top equation 33.5 from both sides, I'll end up with FGH cosine of 26.565 plus FCH cosine 26.565 equals a negative 33.5. And then in the other equation, I'll have, if I subtract 16.75 from both sides, I'll have FGH sine 26.565 degrees minus FCH sine of 26.565 degrees equals negative 16.75. Now, when we're working with simultaneous equations, the way that we've learned how to solve that is by elimination, by combining the two equations together in such a way as we can eliminate one of the unknowns. And my target for elimination here would be FCH, because FCH has a positive in one equation and a negative in the other. It'd be easier, though, if FCH was just FCH alone and not FCH times the sine of 26.565 or the cosine of 26.565. It'd be easier if I could force the numbers here that are multiplying the unknown values to be 1. Well, fortunately, we have a way of doing that. We can divide. Remember that we don't change an equation if we divide each term by the same number. If I take this first equation and I divide each term by the cosine of 26.565, it's just a number, the cosine of 26.565, it won't change the equation at all, but it'll clean it up a lot. It'll make the number ugly, but at least the variables will be nice, because cosine of 26.565 divided by the cosine of 26.565 is 1. Over here, I get negative 33.5 divided by the cosine of 26.565. And if we plug the numbers together on that, we get negative 37.454. We can do the same thing in the other equation, the y direction equation, except we divide through by sine. Dividing through by sine will knock out the coefficients of our unknowns and give us kind of an uglier number on the right. So if we divide.
So is it safer to just divide by sine 26.25 or 26.525, or you know what I mean?
Yep.
Or like I converted it to a decimal first. Is that wrong?
No, I usually prefer to do it by hand first this way and then go to the calculator once.
Okay, copy.
Just to do that division.
I didn't know if there was like a reason we weren't doing it.
It's more just habit, my habit personally of not calculating things until the end.
Okay.
Not running to the calculator until I have to.
Understood.
And that way, I mean, you're writing the same number of digits. In fact, you're writing more because you're writing the sine and the cosine. But at least that way, I don't run the risk of messing up certain things. I know these are all the same, so I'm just going to cancel them out. But here we have 16.75 divided by the sine of 26.565. So we get 16.75 divided by the sine of 26.565. And we get a negative 37.454. How about that? So to clean these equations up, to write those up a little more nicely here, we've got FGH plus FCH equals negative 37.454. And we've got FGH minus FCH equals the same, negative 37.454. Now, I know we haven't dealt with simultaneous equations for a little while, and as the ones we've done in the past have been a little bit harder than this because they had different values in front of the unknowns. Here we had the same values in front of the unknowns, so it was a little bit easier. But make sure you go back over that and are clear on what you had to do here to get a simpler set of equations to solve. All we did was divide through the x direction equation by cosine of 26.565. That knocked out these ugly numbers here and just gave us one number to deal with. We divided the second equation, the y direction equation, through by the sine. And that gave us a nicer equation to deal with, but preserved the sign difference between FCH in the x direction and FCH in the y direction. Because now, to solve these, we can add the two equations together. On the left side, when we add these two equations together, we have FGH plus FCH plus FGH minus FCH. The FCH's cancel out, and we have 2 FGH equals negative 37.454 minus 37.454. That's a negative 74.908. And if we divide both sides by 2, we get FGH is a negative 37.454 kips. So FGH came out negative, which means our assumed direction was incorrect. So let's go back and look at the free body diagram here. Remember, GH carries a load of 37.454 kips. We assumed it was in tension. We assumed it was being pulled on by the rest of the truss. But we got an answer here in our calculation that says that assumption was incorrect. That means member GH is in compression. So member GH is in compression and carries a load of 37.454 kips. Now that we know member GH, we can go back and plug in and find FCH. And if you're reasonably confident, I know the mathematicians will say, go back to the original equation, plug in what you just solved for, and go and calculate what you're missing. But if these are the same equations, if going down to here, if these are the same equations as the ones we started with, we should be able to go back and substitute into these, and it should still work. So we shouldn't have to worry too much about there being a problem there. If you made a mistake getting from these original equations down to this, then that mistake will carry through, and you'll get a wrong answer no matter what you do. But if you're confident in your conversion between these somewhat uglier equations and the cleaner ones, then you can go ahead and substitute into the cleaner ones. So I'm going to use the first equation here, which was FGH plus FCH equals negative 37.454. And I'm going to plug in the value that I got here of negative 37.454 for FGH. So I have negative 37.454 plus FCH equals negative 37.454. And if I add 37.454 to both sides, FCH equals 0. It turns out the way that this truss is loaded, member CH carries no load. So member CH is unloaded. So member CH, no load, so therefore not in tension or compression. It doesn't mean that member CH is totally useless. Member CH would come into play in different loads. If maybe there was an uplifting load, or if there was some other combination of side loads and gravity loads on it, there would be an issue there. So member CH, no load on that one. So we figured out from our method of sections the three forces that that were missing in our cut. We still have one more to get, but before we jump to that last one, anyone have any questions in getting the three unknown forces here? Remember GH, CH, or BC? All right, so to wrap the problem up, what I would do here is rather than doing another cut through the truss, I would just do method of joints at joint B. Joint B is right here. It has three forces acting on it. It has member BC, it has member BH, and it has member AB. So we can figure out what load is on that member BH. So let's draw the free body diagram here. First, always draw the forces you know. We know member BC's force. Member BC carries 35.5 kips in tension. And remember what tension means for method of joints. Method of joints for tension means that the joint is pulled toward the member. So if member BC is over here, it's pulling joint B in toward the middle of member BC. So the force that joint B feels for member BC in tension is 35.5 kips to the right. Then we've got some force due to member AB. And then we've got a force due to member BH. Those are the only forces acting at B. So that's our free body diagram for joint B. Now we only need one of those two unknowns. We don't really care about AB. It's not in our list, so we don't need to solve for it. AB only shows up in the X direction equation. We only really need the Y direction equation here. So we do our sum of forces in the Y direction, and all we've got in the Y direction is FBH. Now if joint B is in equilibrium, FBH must be equal to 0. The sum of forces in the Y direction must be equal to 0. There's only one force in the Y direction. If there's only one force in the Y direction, and you have to have equilibrium, that one force must be 0. So it turns out for this one, member BH also carries no load. So the only members on that side of the truss that are carrying load, at least in the part that we looked at here, are members BC and member GH. And again, you can kind of appeal to the bending idea to give you some explanation for why the members are in tension or compression. If we pushed down on the middle of this truss, it's going to try to make the middle fall. It's going to essentially bend it downward like that, which is going to put member GH into compression and stretch out member BC. It's going to put BC into tension and GH into compression. The top chords of a truss under gravity loads are generally under compression, while the bottom chord is generally under tension.
So before, when you had said that no matter how many joints we're looking to solve for, we only need one less than the total, correct?
Yeah, when you're doing method of joints.
Yes.
Yep.
So that being said, could we continue just go from joint to joint to joint to figure out every possible load, or is the other method better?
In principle, yeah, you could, and it's generally a matter of when you want to find out everything. If we wanted to know every single member, what force was carried by every single member, it's a matter of personal preference, whether you use method of joints or method of sections. You're going to end up
Okay.
using the same number of steps. It's the same, it's computationally the same difficulty of calculation. But if you only need a subset of them, generally method
Okay.
of sections results in fewer steps. And then if you can't get everything you want in one cut with method of sections, usually some combination of method of sections to jump you into the middle of the truss, and then method of joints to get you going out further will help you.
Gotcha.
All right, any other questions on that one?
Actually, could you run me through real quick on how we found the angles for the first free body diagram?
Okay, so the 26.565.
Right.
All right. So one of the ways I looked at it here was I looked at it as this angle right here. And I zeroed in on this big triangle,
Uh-huh.
the big right triangle here.
Right.
Because I know the whole span is 24 feet and this is symmetric, half the span is going to be 12 feet. So this base of this triangle is 12 feet. It's 6 feet high. So inverse tangent of opposite over adjacent, 6 feet over 12 feet,
Right.
gives me 26.565.
Okay.
Now, you could have also done the same here, saying this is 3 feet and this is 6 feet. So, as I said, there were 4 bays at 6 feet each. And it's not too hard to argue that since you got the same slope here, if you go halfway from joint A toward the middle, you'd have to go halfway up too.
Right.
So it's 6 feet and 3 feet, same angle.
Right.
And then do you have more of a question as to how these two angles came in?
Nope. That's I just needed the start. Thanks.
All right. Any other questions? All right, that's the content here for tonight. Let me see, go back over to the slides for a moment here. So that's our content here for the evening. Next time on Monday night, we'll be taking a look at what we call frames. Frames are a more general structure than a truss. We relax a couple of the constraints that we have on trusses. Now that means we can't necessarily answer the same questions. In fact, it makes tension and compression something we really can't define, but we can still solve some interesting problems with them. So we'll take a look at what frames are, and that'll round out our structural component of the course. Anyone have any questions? All right, if you're sticking around for the practicum session, stay on the line, I suppose. Go
I
ahead.
had a quick question if you
All right,
got
go ahead, Mark.
So test schedule, are we going to try to stick to the same syllabus, and how do we plan on handling test situation?
Let's see. It's a good question. I can't say that I have a good answer for you yet on that. Um,
Okay.
the the basic issue is going to be how we handle exams. There we go. How we handle an exam. Obviously, I can't do an in-person exam right now.
Right.
There isn't going to be a way to do that. So it's going to have to be some form of take-home exam. How exactly that's going to be handled, I don't know. Whether or not I can give you uh, some sort of problem to solve online where the numbers change or something like that, or I just post something and trust that you will uh, do it in a reasonable amount of time in a reasonable way. We'll see where we are when we get to that. But in any case, we will be doing some testing. I don't know, given the delay, whether the testing will end up being exactly the same as I had intended, but it will be it'll be reasonably close. We'll be doing a second exam probably in 2 weeks. Um, and
Is that gonna cover everything?
it will cover just method of joints, method of sections, and frames. It'll just be the structural part of the course. And then we'll be covering strength of materials in our last bit. That's shortened a little now because we've missed a week. But so what I might do on that is only include that on the final. So our final will cover everything, including the strength of materials.
You know what you could do? Just throwing this out there. What about a team test?
Well, I don't know
Everybody
about that.
works together. Come on, like a Jeopardy action type thing.
There we go.
Make it fun. As long
I'll
as
have to
we're
think about that one.
I was
All
just gonna
right.
say, have us watch us on video while we're doing it.
Yeah, I mean,
That's
I
kinda
could do
weird.
that, but
Yeah, but we're watching him.
I like Mark's idea. I'll buy the beer.
There you go.
right now I'm leaning toward just mostly because I suppose I'm lazy. I really don't want to do anything different if I have to, and it would take a lot of effort to put this online. And given the situation and all of that, I think what I'm probably going to do is just put the exam on the website, have you download it, work it, and send in the results. So we're just going to shift everything to kind of a take-home sort of thing.
Works for me.
I think it's the simplest thing I can really do, and then I'll just have to trust in everyone's personal integrity that they will work on it in a way that would be consistent with testing it in class.
We could put a timer on Zoom.
In principle, we could, but I'll think about that, see what options I have as we get closer. But for now, that's probably what we're going to end up doing.
Copy. All right.
Any other questions? All right. If you're not sticking around, I'll see you on Monday. And if you are, come back about 10 minutes or so. I'll put up a couple more problems.
All right. I'm taking off. Have a good night, guys.
All right. Have a good night.
Later.
Oops.